We have not begun to imagine what we could possibly be encountering. The most common misconception about the Big Bang is that it was an explosion in space. But it's so much more interesting than that. Our elements are literally made in the cores of stars.
Wow.
This is why we're stardust. We are just a tiny bit of residue left over from the Big Bang, a little bit that sparkles in a sea of darkness.
Tell me why I should believe we're the only ones that are intelligent in this galaxy.
I wouldn't say that you should believe that.
Dr. Janna Levin is an astrophysicist and professor at Barnard College. She specializes in black holes, chaos theory, and quantum and theoretical physics.
Janna's going to explain why so many people have a hunger to understand our place in the universe.
The supernova is one of the most important things that happens in the universe because it expels all its material. And that material has carbon, oxygen, nitrogen. And out of that, you can make a rocky planet. We see hundreds of billions of galaxies, and they all seem to have supermassive black holes. What we've discovered is that most stars have multiple planets like we do. So if you think about the vastness of the stars and the numbers that we talk about, there are more planets than that. So now our search for life becomes very interesting. There's two very different divergent paths. One is that we will kill ourselves, or we fundamentally change as a species. It's the only possible future for us if we're going to survive.
Are we all going to fall into a black hole?
Well, here's the thing.
Hi, I'm Mayim Bialik.
I'm Jonathan Cohen.
And welcome to our breakdown. We're going to be talking today about the nature of essentially desire. And it's the nature of our desire to understand the things that are so much bigger than us and what that means for our lives right now. Have you ever thought about how you got here? Have you ever expanded that out to how did everything get here? Have you ever expanded that out to how did everything outside of everything get there and what existed before we got here? We have the perfect person to talk to about this.
Some of these fundamental questions are so important and are on the rise these days. So many people are curious about this because it's scratching this deep fundamental itch to help us understand ourselves, the world around us, and we're looking for purpose and meaning in a way that these conversations about the solar system, what's happening in the universe around us, are starting to help us answer.
We're going to be talking with Janna Levin, an astrophysicist who is a professor at the Barnard College of Columbia University. She's also the founding director of sciences at Pioneer Works and the founding editor-in-chief of Pioneer Works Broadcast. She's a Guggenheim Fellow, and she specializes in black holes. She's written this delightful book, Black Hole Survival Guide, and it's very, very cute. And there's also beautiful artwork by Leah Halloran. But what we're going to ask Janna to do today is to explain how we got here, why we're here, where we're going, are we alone, and why should we care? It's a deeply moving conversation. It's also a deeply intellectual conversation. And Janna's going to explain why so many people have a hunger to understand our place in the universe in a way that we never have before. And we now have the capability to understand our place in the universe in a way that we never have before.
Don't forget, there's a big part of this conversation, exploring black holes, the new information that is available about them only recently, the scientific breakthroughs that are happening, and how that information shapes everything else you discussed in terms of our role in the universe and the role of black holes in the orbiting of the Earth and the formation of our galaxy.
In case you're not sure if you want to understand black holes, I'm going to ask you to take a leap of faith. You want to understand black holes, and the best person to do that is Janna Levin, who joins us in person. Janna Levin, welcome to The Breakdown.
Break it down.
Thanks for having me here.
We're very happy to have you here in person.
Yeah, in person's nice, right?
It's nice. It's a different kind of conversation. And I would say that you are an expert in some of the most difficult things to comprehend.
Somebody's got to do it.
Correct. And I think it feels especially appropriate to get to have this conversation in person because I feel like there's going to be a lot of, wait, what?
Right.
Can you go back? You know, one of the really special things about the work that you do, besides what you do academically, which is very significant and important and all the good things, you communicate very, very complicated concepts to people in a way that is very beautiful and it's very lyrical. And in particular, your Substack community is very, very devoted, dialed in, and locked in to wanting to understand things, not just in a scientific way, but in a beautifully scientific way.
Yeah.
What would you
I
say
appreciate
your
that.
mission is, and how did you arrive there?
I think with most things, I'm pursuing stuff selfishly because it appeals to me. And the hope is just it'll appeal to others as well and people will join. And I think that's always surprising and astounding that people do join. But there's a sense in which it kind of hits people in the solar plexus, even if they're not technically understanding everything you're saying. I don't really want to lean into expository writing as though there has to be every detail transmitted. So at the end, there's some kind of scientific comprehension. It's really more describing the view from a certain climb that you've had the opportunity to ascend. And why not share that view with people as best you can? And part of that view and why it's meaningful to us is the personal and poetic interpretation of it. And I think that's the sort of resonance. People want to understand the Big Bang, black holes, dark matter, the universe, but they also want to understand how to sew that into the fabric of their own experience.
Why do you think that this information now has sort of struck such a chord and people are so hungry to try to understand it? Because as you said, like the details are way beyond my comprehension, beyond most people's comprehension, and yet it's still fascinating.
Yeah, I think that's an interesting question. I do think the appetite seems to be growing more and more. Maybe it's word of mouth, people sharing that this changed my perspective. How many times has that happened to us? We hear the same things over and over again, even sometimes in science. You know, our discussions medical science or climate science can circulate around the same things. And there isn't a sense of, there was a shift for me in that moment. I think when people start to experience that kind of, wait, what? What does that mean for where we are in the universe? What are we? We're a little less than 5% of what's out there. And that they share that the way we do other kinds of revelations. And I think it's this kind of contagion that's been very organic. It's not coming from, advertised, intentional networking. It's coming from word of mouth.
I think there's also something that we talk a lot about that just occurred to me in this moment, is that thinking that we're only 5%, thinking that there is so much happening that is complex, way beyond our understanding, that there's all these processes and systems happening in the universe and the galaxy. It's like makes us have this sense of awe and wonder and like what else could be possible that we may not have any concept of.
Right. I think it's this interplay between the sense of the incomprehensibility, the kind of pleasure of the humility of the astronomical perspective, understanding where we are in this enormously complex scheme and reevaluating, reassessing that, but also the sense of the integration, too, that somehow we're all connected. So it's not just, I feel so insignificant, and that's kind of the end of the analysis. It's really that there are these universal themes. There is this unreasonable power of fundamental principles. For instance, that we all can radiate according to a perfect universal law, like Planck's law. We all are hot bodies, and we all emit light. And that also can describe the sun. It can also describe a hot rock. It can describe an incandescent bulb. It can describe the Big Bang. That universal connection is profound.
It feels like that also makes people feel like there's some order to the chaos, that things are following some sort of rules, even if they're too complex for us to understand, even if our understanding is still developing, that maybe all this chaos is not only chaos.
Absolutely. I mean, the entire paradigm of theoretical physics, cosmology, trying to understand the universe on the largest scales, is to distill our understanding of fundamental law to the simplest principles and to the shortest list, the one mathematical sentence from which everything can be derived in principle. So the goals are very reductionist, but the complexity that emerges is still enormous, and that you can have this kind of complexity emerge from something that really might be unified in some really profound way, that we are all fundamentally the same kind of, maybe it's a string, maybe it's a particle, maybe it's a membrane, but that it all maps back to this unity, I think, is really the whole paradigm. And so we're trying all the time to cut through the complexity and try to see that one law, right? Find that universal description. It's really hard.
Said many physicists over time.
Yeah, right now we're operating at the edge of our understanding. We really are. We're looking at the possibility of extraspatial dimensions, that the universe isn't all we see. And it's hard, but the intention is, on the other side of that obstacle is some simple description that we can take as a starting point, literally, of the universe.
I'm fascinated by the statement, the universe isn't all that we see.
Yeah. Well, maybe I should say what we see isn't the whole universe. That's probably the more accurate way to put it.
And we know that because our tools have changed drastically, even in the last 50 years.
Yeah. And as we were just saying, we had this stunning discovery in the past few decades that we're just a tiny bit of residue left over from the Big Bang. I mean, a little bit that sparkles, right, literally interacts with light, is luminous in a sea of darkness, of matter and energy that can't be seen, that doesn't sparkle, doesn't interact with light.
Mayim Bialik's Breakdown is supported by MSI United States.
Hey friends, it's Mayim here, and I'm here to tell you about an organization that's doing incredible work around the world, MSI Reproductive Choices. In 2024 alone, MSI helped 21.5 million people access reproductive health care. That's everything from contraception and safe abortion to maternal care and cancer screenings. And here's what really, really struck me. 1 in 5 of their clients are under 20. That means millions of young people are getting the tools to make informed decisions about their futures. And without MSI, pregnancy-related deaths in the countries they serve would be about 15% higher. They also have trained 12,000 healthcare workers and supported over 8 million people through local health systems that they helped strengthen. That's real impact and real lives saved. This organization is donor-funded. They get no help from the U.S. government, so they're asking us for support. It's very inexpensive and you can have a huge impact. $6.50 per year of contraception is incredibly transformative. You can help girls stay in school, help women stay employed, and help them live healthier lives. With $65, you can give 10 women contraception for a year. To give, text my first name, Mayim, to 511-511. Text MAYIM to 511-511, or go online to msiunitedstates.org to learn more or to give. That's M as in modern, S as in safe, I as in informed, msiunitedstates.org. How many women will you help? Please give generously. Text Mayim to 511-511 today. Text fees may apply.
Mayim Bialik's Breakdown is supported by Calm.
Is anyone else feeling like this year has flown by way too fast? That where did the time go? Anxiety is real, and it can leave you feeling scattered and behind. Calm gives you permission to slow down, even when it feels like everything is speeding up. Calm's the #1 app for sleep and meditation, and it's here to help you feel better. If you're feeling like you could use some support navigating life's ups and downs, get the relief you need with Calm sessions like guided meditations to help you work through anxiety and stress, boost your focus, build healthier habits, take better care of your physical well-being. They also have sleep stories, sleep meditations, calming music to help you drift off to restful sleep quickly and naturally. Also, grounding exercises, we're big on those, help you reset and relax if you're feeling overwhelmed. They also have expert-led talks to help you handle grief, improve self-esteem, improve relationships. The Calm app puts the tools you need right in your pocket, so stress and anxiety relief is always within reach. Calm has over 2 million 5-star reviews, and they can help you stress less, sleep more, and live mindfully. Calm your mind, change your life. Calm has an exclusive offer just for listeners of our show. Get 40% off a Calm premium subscription at calm.com/break. It's an amazing value. Go to calm.com/break for 40% off unlimited access to Calm's entire library.
Calm.com/break and tell Calm you heard about them from us. Mayim Bialik's Breakdown is supported by Thrive Cosmetics.
The transition from summer to fall is a very special time in my house. It's when cozy baking season begins and everyone says, stop baking. And the delightful spiced scents of cookies and pastries are a simple, intentional way to make home feel like a cozy, delicious sanctuary. Small traditions that mark the changing of the season feel good, and that includes updating your makeup look. From a simple, just gotta get out the door routine to festive fall glam, Thrive Cosmetics is your go-to for completing any fall look. Every product is 100% vegan, cruelty-free, and made with clean, skin-loving ingredients that work with your skin, not against it. We love that Thrive Cosmetics gives back to a ton of causes that are important to so many of us. With over $150 million in product and cash donations to 600+ giving partners, your purchase directly fuels real impact, and that's beauty with purpose. One of my favorite Thrive products is Liquid Lash Extensions Mascara. It's a vegan tubing mascara with over 40,000 5-star reviews. It's sweat-proof for the summer with 6 shades that last all day without clumping. Actually, where we live, it's sweat-proof year-round. No clumping, no smudging, no flaking. Plus, it's easy to remove, slides right off with warm water without yanking out your natural lashes. Complete your fall look. Go to thrivecosmetics.com/MBB for an exclusive offer of 20% off your first order. That's Thrive Cosmetics, CAUSEMETICS.com/MBB. It used to be that this field was very, very distant from really every other field. And even when I went to grad school, 8,000 years ago, there was this notion that those are those people studying that over there.
Yeah.
There really wasn't a lot of conversation about overlap. And, I in studying cognitive neuroscience, we got to talk to people in the philosophy department, and that was considered crazy, right?
Right.
But to even have any conversations that might overlap, right, about consciousness, about reality itself, about our perceptions of who we are versus who we actually are, those are things that do now seem to have all of this overlap. And these are kind of those conversations that you get to help people have. So maybe you can start us off really basic. How did this get here? Meaning, where did we start and how did we get to this planet?
So you could start the story with the Big Bang. It's the idea that the universe had a beginning. It's quite fundamentally observable, which is strange. And then I'm going to kind of reverse some of what I'm saying. But imagine the Big Bang really is the ultimate beginning. It's the beginning of space and time.
So what was before then?
Well, so at some point you have to say, if I really believe in the relativity of time, I really believe that time is a mutable aspect of the universe, and it's not this rigid stage against which everything unfolds, but it's actually something that can deform. Then I have to, by those dictates, say that might not be a meaningful question. Because if the time really originated in that moment, it's like saying, what's north of the North Pole? You're just wrapping round again. And so there's a way in which space-time can be a continuum in a profound sense, but also have a beginning, not be stretch infinitely far into the past.
Okay, so very hard for a lot of people to wrap their heads around. Okay, so something happened.
Something happened.
Yes.
So let's talk about the Big Bang. So the most common misconception about the Big Bang is that it was an explosion in space, that there was this large space and time just waiting around for this explosion.
That's how our brains can frame it.
And that's natural to have that first thought, but it's so much more interesting than that. Really, the space itself is bursting out of that primordial event, which we don't fully understand. What kicked it off? Is it just randomly, occasionally, some quantum event happens and a universe bursts into existence? And that might be the case. So going just a fraction after it happens, we do understand it pretty well. It's not an explosion in space, which would have an identifiable center, like a star exploding. You'd be able to see where the center had been. It's not like that at all. The explosion happens everywhere simultaneously. We are now in the center of what was once the Big Bang, as is another galaxy on the edge of the observable universe. We were all at the center. The center was everywhere. And that is very perspective changing. So the center itself stretches, explodes, and
how do you
and
know
it happens
this?
everywhere.
How
That's
do we
a great
know this?
question.
But I want you to explain.
Yes.
I'm not trying to be like, how do you know? I'm saying, can you explain in layperson's terms, how can we understand this event with this kind of specificity?
Right.
Wow, what are you looking at?
Right. So this was first proposed when people were looking at Einstein's theory originally back in 1916, when he first wrote down the general theory, which was describing space-time. There were scientists who went to Einstein and said, do you realize your theory predicts that the universe is actually expanding? And if you run the movie of this expanding universe where all the galaxies are moving away from all the other galaxies, literally like the space between us is stretching. That's the way to think of it. The space between us is stretching everywhere.
All of a sudden there was like, and I'm putting my hands together, this, and then all of a sudden it just expanded into the galaxies and universes that we understand.
Right.
I mean,
in
even going like this is actually not accurate,
Right.
because that's indicating that there was something that came
together.
Right.
So there is confusion about whether or not the universe is infinite, which isn't helping. But if we imagine that the universe is finite and there's only a certain amount of space.
Right.
Of space itself, let alone the stuff in it. And then we're imagining that every single region is expanding equally, literally. Just one way to imagine is often taught or told is that imagine we live on the surface of a balloon. Only the surface. The surface is our whole reality. As that balloon stretches, the distance between, let's say, stains on the balloon gets greater and greater and greater, right? And in that sense, the surface of the balloon has genuinely gotten bigger. And the problem with that analogy is it sure feels like the balloon's expanding into something, the 3 dimensions that the balloon lives in. And we're trying to do the exercise of forget this higher dimension, just you live only on the surface of the balloon. All that matters is the surface of the balloon. In our 3-dimensional experience, it would literally mean, from my point of view, I would see every galaxy move away from me as though I was at the center of the entire universe. But if I displace myself to a galaxy billions of light years away, it will have the same impression, that everything is moving away from it. And there is no place that you could find that would win the controversy, that could, in unambiguous terms, prove, aha, I'm at the center of the explosion. Everywhere you go, you appear to be at the center, but that's the same for everyone else as well.
And that's narcissism.
Well, it's one of these, it's narcissism, and then it's, again, that shift in the astronomical perspective that kind of makes you realize, it's very much the Copernican idea that we are not at the center. We are not at a special place. So,
okay, so get back to how do
we know?
You know?
So Hubble observes this, which is Edwin Hubble, the astronomer after whom the famed satellite is named, the satellite being more famous than the astronomer now, in Mount Wilson nearby.
Yeah.
In these incredible, what was at the time the largest telescope in the world, was not even sure there were other galaxies out there. So even if you just start with that, we talk about our Milky Way galaxy. It's a collection of hundreds of billions of stars. It is this beautiful spiral pattern. That's our single galaxy. When Einstein was working, when Hubble was working before his discovery, they weren't sure there were any others out there. It could just have been us. It's kind of like not knowing that other stars are suns, and suns have planetary systems. This, how big does it scale up? How unique are we? And there was some...
Turns out not
very. And there was some, questions. Maybe there are these smudges on the sky. They look like nebula. Maybe those are entire galaxies.
And we're looking with telescopes now.
With telescopes.
We're like zooming in.
Right. So this is the 1920s, like around early 1920s. And Hubble looks at one of these famous objects in the sky, and he realizes by studying certain stars in that system that these are stars he understands so well from someone else named Henrietta Leavitt that he could place its distance. It was like knowing that you have a light bulb in your room. You can tell if it's up close or far away because you know that light bulb so well. So these stars were like these standard candles. He was able to say, oh, that is a very bright object, very far away. And by pinning it to the galaxy or the nebula, he was able to say, this is another galaxy. It's an entire galaxy. It's millions of light years away. It's outside of the Milky Way. And it was Andromeda, which I know you've made jokes about. The Andromeda galaxy is a galaxy that's very near to us. It's one of the only galaxies that's coming towards us and not going away, because actually we're going to collide with Andromeda one day. And
What does she want from us?
yes, she wants to make a bigger black hole at the center of our galaxies.
So drink the good wine.
Right. In about 6 billion years, a few billion years. So that first discovery, all of a sudden, the universe becomes much bigger. And it's full of galaxies. And then he proceeds to observe these galaxies that he can see. Now that study's gotten incredibly, 100 years later, we're really good at that. And they're all essentially, statistically, moving away from each other. They're certainly all moving away from us according to the famed Hubble's law, which is exactly the law you would expect if it was the space stretching between us and not the galaxies physically racing around.
And that relates back to an understanding of the Big Bang Theory.
So the energy of the universe is so high energy in this initial moment, really scales that we can only fantasize about ever reaching. Our most powerful colliders that we reach, incredibly high energy scales, are still trillions of times less energetic than anything we could possibly imagine from the Big Bang. And so here you have this hot, frothing universe. Matter is in its highest quantum state that we don't fully understand. But our predictions from back the first few minutes is so excellent. We can predict abundances of like hydrogen and helium, certain trace elements that come from the Big Bang. Most of this in your body comes from the Big Bang. And we have incredibly accurate understanding of that early synthesis of simple elements. There's also the light left over from the Big Bang is measurable.
What does that mean?
Yeah. So it was we were talking about hot radiating.
It was a hot mess
yes,
is what it was.
It was a hot mess, and it radiated according to that universal law.
Yeah.
And the light has been cooling as it comes out of this energetic event. Space itself feels the pressure of this creation of all this energy, and the space actually expands in direct reaction to this pressure from the matter in the universe. And so the universe comes out expanding and
bang.
And a bang. And it's hot, very hot, as we're saying, trillions of times hotter than anything we can conceive of recreating here on Earth. And then it cools over the past nearly, not quite 14 billion years.
But it produces light when it's that hot.
It produces light when it's that hot. And then eventually, the light is scattering off the matter, and it's all in this chaotic mess that you were describing at the beginning. And it kind of equilibrates. It comes to this really beautiful, perfectly hot room, space. And eventually the matter sort of decouples, breaks away. It gets so cold, it starts to fall into little seeds that formed in the early universe, and those become, after a very long time, the galaxies. But the light is left. It just doesn't tire. It doesn't go away. It doesn't get absorbed by anything. It fills all of space. And so we literally have a 13.8 billion year old hot bath of light that permeates the universe in every direction. And by now it's cooled tremendously. It's now only a few degrees above absolute zero. It's just cooled with the expansion of the universe. But we go out and we measure this light. And it is unbelievable, stunning observations. One of the most important observations came back in the 1980s from a satellite called COBE. And it was such a perfect measurement of this hot body that clearly had all been together at one point in time, that it drew spontaneous applause. It was like one of those Nobel Prize winning moments. And so we see the Big Bang. We see its afterglow.
Okay, so if you don't mind, I'm going to have you keep walking us through this.
Yeah.
So hot, bright, cooling.
Yes.
Take me to, so now I'm kind of grooving on a galaxy. Take me to planets.
Right. So
take me to these 8 or 9 if you're old.
Right.
Poor balls
Pluto.
of stuff, and there's an orbit, and they're kept in orbit, and like what?
Right.
How did that, which sounds like beautiful and chaotic and entropic, right? How to get me to planets?
Right. So when the matter, the material in the world starts to cool and decouple and fall into tiny little lumps that were seeded in the very, very early universe, eventually entire galaxies form. They may well form simultaneously with black holes. There's probably a supermassive black hole that forms in the cores of every single galaxy. We see hundreds of billions of galaxies. That's just what we can see, just as far as our instruments are able to probe. The universe is just full
Say
of
that
these.
Again?
So
We see hundreds
of billions of galaxies.
Of galaxies.
And they all seem to have supermassive black holes, as far as we can tell, at their cores. That's black holes, millions or trillions even sometimes, the mass of the sun. And they form together with the galaxies. And there's this... Yeah, you're like...
Well, I'm trying to place this also in terms of like, most of us, the farthest we know is... My very educated mother just served us 9 pizza pies. That's the order that we learned the planets in back in the 80s. Most of us kind of stopped there, right?
Right.
We're the third rock from the sun, like blah, blah. So take me to... So we get these gatherings of elements.
Right.
Elements,
Yes.
naturally occurring elements that form for some freaking insane reason, distinct planets, each with a very different character, different personalities.
Yes. Very extreme. So how do we get there? Because that takes a while.
And how do I need to incorporate black holes into this story?
Yeah. So let's start with let's get to the planets. So planets cannot form out of the primordial material from the Big Bang. It just
to be
can't.
God. No, just kidding.
Right. So there's always a place where you could fill in the gap. And remarkably, I'm sure you've heard the story, we are stardust, or we are made in stars. We need those stars to make heavier elements. So stars form out of the primordial stuff, and they can be made of the simplest things like hydrogen, pure hydrogen stars. And they're burning thermonuclear fuel. They're thermonuclear furnaces. So they're fusing hydrogen and they're making the periodic element, the periodic table of elements.
What is the mechanism for that, though? Because like when people look at the periodic table, it's like if you take hydrogen and you put 2 of them with oxygen, you get water, right?
Right.
Can you explain what a star actually is? Like it doesn't have a motor.
Right. So the oxygen doesn't exist in the early universe. I mean, the periodic table of elements would be empty. It would be theoretical. It would have some hydrogen, some helium, which is next up, very light element, and maybe tiny trace of some other things. So the star, it's so heavy that if you've ever heard of critical mass for nuclear weapons, one of the big problems they had to overcome in designing a nuclear weapon was they had to have the case implode. And they had to have the case implode because it had not reached critical mass. It's very hard to put things under the kind of pressure that it needs to be under to ignite a thermonuclear reaction. And the sun does this naturally because it's so incredibly heavy in its interior that it reaches these staggering pressures and temperatures that we can't reach artificially. And it very comfortably burns fuel, thermonuclear fuel, and just literally Earth's full of thermonuclear fuel. So stars take that hydrogen, they start making oxygen, carbon, these heavier elements that simply aren't made anywhere else.
Mayim Bialik's breakdown is supported by Blissy.
I was this many years old when I found out that traditional cotton pillowcases can cause hair damage or skin breakouts. I literally lived my whole life without knowing that. But now I can rest easy, literally, with Blissy. Their pillowcases and hair accessories are better than satin. Satin's made from synthetics, which can be rough on hair and skin, and it's cheap for a reason. Blissy's pillowcases were voted best gift of the year of 2024. Their pillowcases will give you healthier skin and hair in weeks, reducing fine lines and wrinkles, eliminating frizz, protecting color-treated hair, even preserving that incredible hairstyle that you managed to nail this morning. Blissy is dermatologist tested and recommended. It's clinically proven to not clog pores, unlike cotton. It has naturally hydrating silk fibers, keeping skin moisturized all night. They're also antibacterial and hypoallergenic, easy to care for. They're machine washable. And they have over 70 colors, including a new Wicked and Harry Potter line. It's a good thing, I haven't posted a messy bedhead in a while. With Blissy, it'd be hard to find a messy bedhead. I look exactly as perfect as when someone did my hair and made it look good. Blissy pillowcases are also naturally cooling and breathable, no more sweaty nights, which means better sleep. Because you're a listener, Blissy's offering 60 nights risk-free plus an additional 30% off when you shop at blissy.com/breakpod. That's BLISSY.com/breakpod. Use the code BREAKPOD to get an additional 30% off your skin and hair. Well, thank you.
Mayim Bialik's Breakdown is supported by Blue Land.
Are you secretly cleaning with microplastics? If you're using detergent pods, your clean might not be as clean as you think. That's why we've made the switch to Blue Land across all the cleaning products around our house and the podcast studio. Their products meet the highest standard of clean. They're effective, gentle on our family, and gentle on the planet. Blue Land was named an EPA Safer Choice Partner of the Year. From cleaning sprays and toilet bowl cleaner to dishwasher and laundry detergent tablets, Blue Land's formulas are 100% microplastic free, made with certified clean ingredients, free from chlorine bleach, free from harsh chemicals that are safe to use around family, pets, and plants. I love not having to choose between what's safe and what actually gets things clean. Blue Land makes it easy to make sustainable choices. Their hardworking, clean products allow you to do better for your family and the planet. They're independently tested to perform alongside major brands. They're free from dyes, bleach, harsh chemicals, and they're certified by EPA Safer Choice certified, EWG verified, Leaping Bunny, USDA bio-based, B Corp. We love Blue Land because we love getting things clean while being nice to the planet. And I'm one of those people that's allergic to every cleaning product that I try, but not Blue Land. So I love the scent, and it doesn't make my whole system say, this must be toxic, because it's not. Blue Land's got a special offer for listeners right now. Get 15% off your first order by going to blueland.com/break. You don't want to miss this. Blueland.com/break for 15% off. That's blueland.com/break to get 15% off.
Mayim Bialik's Breakdown is supported by AG1.
We've had our morning routines down for the past 4 years or so now with a simple scoop of AG1, which supports our energy needs, our skin health from within, digestive regularity, food cravings, immune support, even a healthy mood. And now we want to introduce you to something that's optimized our nighttime routine by improving sleep. AGZ is a melatonin-free formula with clinically studied herbs, adaptogens, and minerals. No artificial flavors, no artificial sweeteners, no added sugar. I notoriously find it difficult to wind down before bed, and so does Jonathan. AGZ helps us with that, and it leaves you feeling more rested, which makes you able to make the most of your days. You mix it with warm water. The herbal flavor puts me in a wind-down mindset, and AGZ is one of the few sleep supplements that have both magtine, that's magnesium L-threonate, and saffron, two very high-quality ingredients at amounts that are supported by research that support the body's need to calm and ease into natural sleep. AGZ's magtine magnesium L-threonate is a clinically tested form of magnesium, which has been shown to improve sleep quality and support cognitive function. Each serving of AGZ delivers 250 milligrams of highly bioavailable magnesium, providing over half your daily value. If you're ready to turn down the stress and focus on the rest, head to drinkag1.com/breakdown. Get a free frother with your first purchase of AGZ. That's drinkag1.com/breakdown. I'm going to do a poor job of this, and then you can feel free to correct it. When we talk about elements, so when you think about what the most basic element is, the reason that it's the most basic is it's the smallest collection, right, of protons, electrons, right, of all the, protons, electrons, neutrons, right? That's usually where most people, at least of our generation, kind of stopped. So what happens is, and this is like one of my favorite parts, of physics, is that you can start adding to them.
Yeah.
And when you add, they add in these rings and they're pretty shapes and it's like really
Right.
dreamy. But what happens is that's what makes the other elements, right? So it's the building blocks.
Yeah.
But at the most basic,
Yeah.
it's kind of like if you had a fireplace and you had perpetual wood that was
Right.
constantly being placed there and you didn't have to place it and it would just keep burning.
Yeah.
That's a star.
The star is going to keep burning until it runs out of fuel,
Right.
until the reactions become expensive. But
Right.
just for your discussion of elements, what's really relevant is just the nuclei.
Yes,
So
right.
so if I have just a single proton floating around in the world, that's a hydrogen atom as far as I'm concerned. Even if it has no electron, it's just the nucleus. It's good enough for me. It's an ionized hydrogen nucleus, and that's mostly what's left over after the Big Bang, just these single protons traveling around. Now, if you want to start jamming protons together into the nuclei to make it heavier and heavier, to make things like carbon,
Right.
oxygen, nitrogen,
Right.
everything, phosphorus, anything you're familiar with, really, iron,
But that takes a long time.
it's really hard to do.
Right.
And it's really hard to get those together into a single nuclei. Planets are made of these elements. And so there's no planets with the first generation of stars. None of the stars in the first generation have any planets because there's no material to make planets out of. There's no rocks.
It's just OG stars.
Yeah, right. There's just simple gas of hydrogen. And so the stars have to do a second thing after they perform their task of populating the periodic table. So they have to explode. If they don't explode, the material is locked inside the star forever. And that's no good for making planets. So a series of things have to happen. The next thing is that stars have to blow up. And not all of them do, but some
How
of them
long
do.
from the Big Bang are we at blowing up stars?
Millions of years. I mean, it's hard to say because it's also kind of argued when is the first generation of stars, and was
Right.
there also a different population that maybe we don't know of?
see,
Did
yeah.
black holes form directly and skip stars altogether in the early? There's a lot of stuff we don't 100% know. But you've heard of a supernova explosion? Probably a very popularizer of songs about
Champagne
supernova.
supernova.
Yes, there you go. The supernova is one of the most important things that happens in the universe because it expels all its material back out, and that material is now has carbon, oxygen, nitrogen, and out of that you can make a rocky planet. And the rocky planet will form much, much later, just kind of this snowplow effect. You have a lot of stars exploding. They kind of act like a snowplow, and somewhere enough material will be kind of pushed together.
And it's round.
Not yet. And it gets reprocessed,
Right.
and eventually under gravity, it starts to become round. That's the natural shape. It's a lot harder to make a gravitationally bound triangle or prism.
We just answered why our planet's round. I
So
think
they
that's pretty
tend,
impressive.
They tend to be round. They rotate, so they get a little
Yeah.
oblate, a little fatter around the equator.
Which is
but-
why when you fly on a plane, you have
Yeah.
to watch the arc of
And it
where
helps
is.
with the tides
Yeah.
and the moon torquing us and things like that. But so we're second generation at the very least, and we know that in terms of the story of stars. And so then you have stars that start to have planets. And the characteristic of the planets has a lot to do with the material that formed it. The previous star, this is why we're stardust. Our elements are literally made in the cores of stars.
Why are they all different?
They're all different. That's actually a really tricky question. It has to largely do with the distance from the sun, and how big you can make certain planets in the inner orbits versus the outer orbits. So the rocky planets are all inner. Mercury, Venus, Earth, Mars.
I didn't think
are
about
all the
that.
inner planets. And then they start to become the gas giants. You start to get Jupiter,
Jupiter.
Neptune, Uranus, Saturn,
I like to say Uranus.
You're welcome to. And in fact, there's a lot of rocky moons around those planets. There's some 200 plus moons in our
What's a moon?
solar system.
It's not a planet.
It's also a good question.
Right, like
We
it's
tend
different
to-
than a planet.
Yeah, we tend
It's
to
not the
call-
sun, that's a star.
Right.
What's the moons? And we're not the only planet with moons.
We only have one. We were pretty
Right.
humble, and that our
Right.
moon probably sloughed off the Earth There was probably a collision event that sloughed off a significant chunk of the Earth as it was still forming and not quite as hard and solid. Yes. And that lump went out and then did its thing and kind of became a sphere and became the moon. Yeah, it's pretty mad. I mean, our moon has lots of wonderful coincidences.
So
we have a very special moon.
We do have a very special moon. My cycle is linked to it, as is yours and all the ladies. But so do other moons do what our moon does in terms of rotation and cycles?
We call a moon more or less a satellite that is trapped in orbit around a body that is trapped in orbit around the sun.
Right, because So
they're not, if there's something behind us in orbit around the sun, we don't really call that a moon because we haven't trapped it in separate orbit around us.
Right.
So we have things that will kind of trail behind us sometimes or orbit the sun, and we tend to not call those moons that are like moon-sized. Or those are more like asteroids, or they're on their own path, or there's probably a planet that broke up that's made the asteroid belt, and that's why occasionally things in this case that it broke into debris, and the debris fills this orbit around the sun. Occasionally a little piece of rock comes our way.
I think humans are the least interesting part of the universe right now.
Yeah. We're interesting because we haven't found any others, and we should absolutely talk about that.
Oh, we will.
But the moons are very interesting here to look for life. So it's not likely to find, we don't think, life on Jupiter, which is very gaseous, and extremophiles maybe could survive there.
I was just going to say, things like us, we expect to see like us on Jupiter.
Right.
Like,
the
what's up?
Fertility of the Earth has to do with the liquid water. The liquid water has something to do with greenhouse gases, our atmosphere, the magnetic field.
I'd like you to confirm this is a very special planet.
It's a very special planet.
If you were to speak
in our list of planets, it's very
so
special.
Can you give us a pretending like you're an alien physicist from another galaxy, and you see our solar system?
Yeah.
What would you say is especially special about this
Earth.
planet?
Yeah. So the Earth is, even though we feel that we bathe in the sun's rays, we're actually far enough away that we should be an ice-capped planet or an ice-covered planet. And the fact that we're warm enough to thaw the oceans, which must contribute to why we're such a fertile and live planet, is because our magnetic field and our atmosphere heats up much hotter than we would be without our greenhouse effect, the ones we want to curb that are running away. But there's a perfect temperate balance that we want from that thaws the oceans. And that, plus the fact that we have carbon from some other star, and carbon is very clingy. Carbon likes to bind with lots of things, lots of clever combinations. Carbon becomes the basis for life here because of the way it tries. Carbon tries over and over again to combine, to bond, to experiment in a way that other elements aren't as, prolific. So we have seen the emergence of a carbon-based life form on this planet. Plate tectonics, actually, interestingly, also plays a huge part in the Earth. I think that we're the only planet in the solar system, 99%. Is true. I'm sure this is true. That has plate tectonics.
Why?
Yes. The rest are just kind of covered with a solid crust or just gaseous. So that's also been very understood to be very important in churning up material from the Earth and keeping things warm. And this cycle has been somehow really participated in the emergence of life.
So even when I was in college, the going story was there was a little pool of liquid in it was like a primordial stew, and maybe lightning happened and it shook up some chemicals and we got prokaryotes. Is that still your definition of sort of how life as we know it evolved?
Yeah, I think it's something like that. There was a very subtle crossing between inanimate and animate. That must be very subtle. One of these things that if we could find how, we still for some reason can't redo this in the lab, right? We can't create a lab experiment where things come alive. But
well, right. We can create conditions that seem to suggest
Right.
and support that if a few other magic things happened,
Right.
we'd have like you can put electricity into goo and see what happens.
Yeah, and
right.
see these things happening. But there probably, if we could get there, we'd be hard pressed to say, is this alive or not alive? And then eventually it's so compellingly alive, right, that it's transition, that we have something that's self-reproducing.
Right.
And we begin to see things like the structure of DNA and the structure, and the cells become complex. And these single-celled organisms, it's really interesting, apparently waffled in the oceans for 1 billion years, more maybe. It was hard for life to get past that and become multicellular. And that step to multicellularity is something we think about when we look at other planets. Is that just really hard? Is that one of these filters or these stumbling blocks that make it hard for life to progress past its simplest phase?
Well, and that seems to be true for our solar system, as far as we know.
I mean, I'd be bargaining on life in moons over planets in the other parts of our solar system. There are moons, for instance, around Jupiter where they have a lot of thermal activity, and there's probably liquid water and things that we don't see really on other planets that we're seeing. So I think optimistically we should be looking a lot at moons.
How many moons does Jupiter have?
Gosh, I don't know how many. It's a lot.
Yeah,
but
is
it
a
has
lot.
some special ones.
There's a lot.
Yeah, there's a lot. I mean,
around
is it more
between
than
80 and
100?
95.
Okay, I was going to say around 100. But there's more than 200 in our whole solar system. They're largely around those guys. They're not around these inner planets.
Right.
And some of them are almost Earth-sized. I mean, they're pretty substantial
What would
bodies.
so I'm just going to ask you to postulate.
Mm-hmm.
Let's say there's life on some of the moons in our solar system, not our moon.
Right.
What would you imagine this life would be like? Is it carbon-based? Is it silica-based? Is it artificial intelligence? Can we just not see it and they're very advanced and we look like ants?
I think it's very likely carbon-based, simple bacterial, single-cell organism style stuff, because we know enough about them to see similarities with our own conditions. The magnetic fields are also really protective for emergence of life. One of the problems in being a human being on Mars is that you're going to get cancer within a couple of years because there's no protection from the cosmic rays and things that are DNA damaging. And the magnetic field is very protective. What gives us those beautiful northern lights is actually important. Right, what we've discovered, and this is also really quite recent, is that planets are the norm. That we weren't sure if planets were just special to our solar system. I mean, you just don't know. And we're saying there's hundreds of billions of stars in the Milky Way galaxy. That's a lot of stars just in our galaxy alone. That's our neighborhood now. This is what Hubble realized. Oh wow, we're just a small place in this much bigger universe. Even in that place, the Milky Way, we think that most stars have planets, and most stars have multiple planets like we do. And that means that there are more planets, more than likely, than there are stars. So if you think about that, if you think about the vastness of the stars and the numbers that we talk about, hundreds of billions of stars in our galaxy, hundreds
more
and
than
billions
the grains
of
of
galaxies,
sand on every ocean,
more than grains of sand on every beach, and we're saying, and there are more planets than that. So now our search for life becomes very interesting.
Tell me why I should believe we're the only ones that are intelligent in this galaxy.
I wouldn't say that you should believe that, but I think belief is the wrong word. I think we have to look at those numbers and with enthusiasm accept the possibility that we certainly should not be. Right, by those numbers. Now, there's arguments that you can
alone,
make.
You mean?
Yeah,
we're
but the
not
numbers
alone.
that's not a very careful study of the numbers. And if we did a careful study, some people would argue, see, we're alone. And if you did a careful study, other people would argue, see, we're probably going to discover life in the next 50 years.
50?
Yeah, I mean, I would say even sooner is a possibility.
Like tomorrow?
Well, I would say even sooner, but you have to understand mostly we're saying bacterial. right? Everything has to start simple.
I
so
want
the
another me.
likelihood-
I want to find out what she's like.
Well, imagine how varied life is on Earth. You know, the jellyfish and those
Algae.
weird algae and slugs.
Mushrooms
and,
are crazy.
Whales. You know, whales and fungi. You know, we should be pretty open to how weird they're going to be. The question is it generic to have sticks, like meaning arms and legs?
The other you is going to have two heads.
Yeah, maybe that works, you know, or their sun doesn't shine in the same waveband that our eyes have evolved to detect, so we would be unable to see each other.
Right. We could be naked mole rats.
Right. Maybe they see in the gamma rays and they just don't see us. We don't emit or reflect gamma
Maybe
rays
they
very
all
effectively.
possess psi phenomenon, and all of these mean materialists are going to be like, whoops. Maybe they all have special abilities.
Yeah, I think we have not begun to imagine freely or liberally enough what we could possibly be encountering. There's some generic things we can ask about. What does intelligence mean? Does intelligence mean a species that wants to control fire, manipulate their environment, make houses, make tools? That could be what we mean.
Cheetos.
Yeah, invent Cheetos, and then explore space. So we have. You were talking about the Substack. I wrote a piece on there called "Whales Don't Want to Go to Mars," and it really just that line really sort of summed it up for me. Whales have an intelligence by all literary and scientific accounts, right? And they care for their young and they communicate.
They grieve. They
grieve, and they're probably talking, singing, and. But they don't seem to have any desire to manipulate their environment. And beyond very small things with garbage that we've foisted upon them, they don't tend to invent tools and then build on those tools and then become so reliant on their tools that it changes their biology, which is what's happened to us.
Right. And other primates do phenomenal things with tools.
Phenomenal things.
And with communication, and we're really not that different, in terms of evolution as, let's say, chimpanzees. However, there's something very special about Homo sapiens sapiens in that we can't live without our cell phones,
right?
As you talk about.
Yeah, and I mean, the domestication of fire is still something our chimpanzee cousins have not achieved. And not only can we capture it when natural fires occur, which was probably the first step in domestication, carting around hot embers and knowing how to use them to warm your hands and then eventually knowing how to make fire. It actually changed, our mandibles are different and our digestive systems, we eat pre-cooked food. We're physiologically incapable of really living without, maybe not our cell phones, but our technologies. And to ask that of other evolutionary tracks on other planets around other stars might be a lot to ask.
So I think then that takes us we have to go out of this galaxy then. We need to step out of this galaxy to have a larger conversation. Because there seems to be, sort of an obsession, right, in this field, right, to talk about the Fermi paradox, to talk about if we haven't seen them, they're not here, or are we being watched in a way that we are not aware of? And, what people like Avi Loeb talk about, if there is something else, which it's very likely that there is, it is likely far older than we are, which means that it has that civilization would have achieved a level of sophistication that is far beyond even our comprehension. Where do you stand on this notion?
Well, I think there's two very different divergent paths that we face right now as an example, the singular example of a technological species that we know of. One is that we will kill ourselves, and it will be a direct result of our sort of tragic flaw that we were so creative and we were so inventive and we had all of those wonderful things, but it was our downfall.
It's very romantic.
It's very romantic. I really believe in tragic flaws. I think an entire species can have a tragic flaw, and as a technological species, I think that's ours. Or we overcome. That there really is, we can overcome our base natures. We can adapt again, fundamentally change as a species, to live in a way where technology is more compatible with nature. I liked this term isotopia, this idea that we don't have a dystopian future, we don't have a utopian future, we have this isotopian future. It's the only possible future for us if we're going to survive for more than a few hundred more years. If we're going to survive thousands, hundreds of thousands of years, even millions of years like other species. We don't have that longevity right now.
Right. We're very recent.
We're very recent, and we're
not
going
doing
to
so
have
great.
to, and not doing so great. Whales don't have the capacity to obliterate all other whales. And we're very strangely poised at that dramatic cusp right now. And it could be that other species develop an isotopia and they become indistinguishable from nature. We will find it very hard to find them because they look so compatible with nature. And ways you can find us are all the leaky ways we're not compatible with nature.
We're leaving our garbage in the universe.
We leave our garbage. We broadcast very sloppily. We're not, we leak a lot. And as we get better, we'll actually be harder to find. So here we are. I mean, I guess.
So if we have not
as
found
a lesson for the others out there.
So if there is life on other galaxies that, let's say, has had a head start, which there's really no reason to believe that they haven't. Part of the reason that we have not found them, which is something Adam Frank talked about with us, part of the reason that we haven't found them is that they're probably much more careful about the footprint that they are leaving.
It could be one of those two. They could also have faced the same fork in the road. I know Adam likes to say every technological species, I'm maybe not saying it the way he would say it, will confront a climate crisis. It's just a necessity of what it means to be using resources from your planet. And if you want to be a spacefaring civilization, then you're going to start to really tax the resources of your planet. And eventually, if you're really sophisticated, like some imaginary civilization that's older than us, that's explored the galaxy, you're imagining taxing the resources of your entire star system and maybe other star systems. And I would say this is like popcorn in the movie theater.
Yes, exactly.
I would say that's what a climate crisis will be, even bigger than a climate crisis, a solar system.
Right.
Environmental crisis. And so I think that either they went extinct or, yes, they became more compatible with nature, not less compatible with nature. And also maybe exploring every other planet out there does not become tenable. And we're talking about scales. It would take traveling at the speed of light over 100,000 years to cross just our galaxy. It would take millions of years to get to the neighboring galaxy.
No, the only way that we could actually fathom interaction or communication would be by some means of travel that we cannot articulate with the current science that we understand.
Yeah. I mean, warp drive is a real thing. I assign it to some of my general relativity students. Well, you can deform space-time with certain energies. We don't know if they exist. Squeeze things closer together, step right across the bridge, and then push them back out again.
Energy workers do it all the time.
Yeah. So there's tricky ways where on paper, at least, we can imagine literally pulling another galaxy closer, jumping across and sending it back out again. We don't know how to do it, obviously, in practice.
Imagining it on paper is the first step.
Yes.
Let's go to what you said about we haven't begun to freely imagine liberally enough. And the idea that the eyes of another intelligent form of life may not have evolved to even see us or us to see them.
Right. Uh-huh.
That's amazing.
Yeah, that's amazing.
They could be here.
Right.
We're right next to them and then we couldn't see them.
Right. I mean, there's presumably if they're made of atoms.
Right.
They still scatter light in the way.
They have to obey some laws.
Right, some laws. But our eyes detect a very, very, very narrow range of light. It's 100% tuned to our specific star. And our star peaks in a certain light, and our eyes evolved to capture that light. And we don't want these huge dishes in our heads that are untenable. So we have these little eyes, and they do pretty well for certain
They're
energies.
pretty amazing.
They're
It's like
pretty
really,
cool.
really cool.
But we can't see infrared and we can't see ultraviolet, and it falls off, So you can imagine a creature that evolves under a different star where their survival required mostly seeing infrared, for instance. They could see us and
It's like
right? They could see us in the
It's like
dark.
Predator.
We'd be like sitting there hiding in the dark, and they'd be like, I can see you.
I mean, my older son's colorblind, and I think he's part of like some evolution that is necessary.
Right. I mean, we don't have some of the senses that even other animals here on Earth have.
Sure.
Right? Because we don't need them as much.
Well, I'm fascinated by that because there are so many different wavelengths, sound spectrum that we are not processing. So to think that this is all that there is somewhat naive.
Oh, absolutely. I mean, I think to think that I'm a believer in an external reality that we are relating to as best we can, but I don't think that yellow exists. That's 100% in our minds. I think that there is this electromagnetic phenomena that it interacts with the atoms in my eyes, and electrical signals are sent telling me the energy of the light. And that is somehow in some, thank you, neuroscience way, leading to the qualia of this experience of this visual world.
That we've decided to add the phonemes to that says this is yellow. And it's broad enough so that your yellow is my yellow, we think.
And we don't know, I don't know what that qualia is for you and all of that, but I do know that there's a way, I do believe that there's an external wavelength of light of that energy, et cetera, et cetera. But there is no way the world looks. That's meaningless. There is no way the world looks. That is in our minds.
Yeah, what does that mean to say that there's an external reality? What does it mean for you?
Yeah, for me, I think that our descriptions, that even the ones that we've been talking about, have such powerful predictive value that even if I'm hanging on at all kinds of human things as well, the math is a human language but that also maybe my neural nets reflect, because it is an external physical reality. I mean, we could probe this too. It's not like our minds dropped out of nowhere. They were formed under the pressure of the laws of physics and thereby reflect the logic of the external world.
Sure.
But even if that is flawed and imperfect and human, I believe it is reflecting some external reality, and that it is true that there are electrons and elements in another galaxy on the other side of the universe, and that we can expect stars are performing thermonuclear fusion.
Before we get to black holes, is this where some of your appreciation for the beauty of this, ability to even fathom any of this, is that where some of that comes from? Because I instantly thought about love, right? What is love then? Like, what's the external reality of that collection of serotonin and oxytocin? Like, what is that? Is there an external reality of what love feels like? Thomas Campbell, I joked, accidentally proved that God existed, right? That if we're seeking a lower entropy and love is that, pathway, where does sort of those kinds of human emotions fit into this kind of explanation?
Yeah, I feel I'm very much a fan of the tenets of evolutionary biology, and I feel a lot of this stuff is traceable to obviously our survival, but that doesn't mean it doesn't have parallels all over in the laws of physics. So, for instance, my first book was How the Universe Got Its Spots, because there's a similarity between hot and cold spots in the light left over from the Big Bang and the bright and dark spots on a leopard's back, how the leopard got its spots. So just because the leopard's spots might have been dictated by some fluctuation in enzymes and some shape and geometry of the developing embryo, doesn't mean it isn't in parallel with other phenomena as enormous as the origin of the universe. And so I think that this idea that we have this love pattern or this poetic disposition could also find parallels in these larger stories.
Which religious people would love, because the notion is, that if there's a God or a higher power, it created us out of love, right? And then we then have these systems that mimic that kind of love.
Right. I think even I myself am very much a materialist, but I feel those beauties. I have the experience of communing with a universe that's 14 billion years old and 92 billion light years across, and that connectivity, I think, for me, comes from the naturalist's position.
How does this all lead to black holes?
Well, black holes have been full of surprises. Really full of surprises. This has been a century for black hole discoveries. A bunch of Nobel Prizes were awarded for discoveries around black holes. I have a piece coming out soon about Roger Penrose, who received the Nobel Prize for his work proving that black holes were an inevitable death state of very massive stars. Before Penrose, people really weren't sure if it was even mathematically feasible to form them, or if it was just an oddity of a specialized circumstance that nature would never actually attain. And he proved that it was this sort of generic death state for very heavy stars. And
so take us from Big Bang, right? From the Big Bang and this sort of explosion and creation, right, at the same time. Where do black holes fit in? Why do we have black holes? What are they?
Well, Einstein, when he was first presented with this mathematical solution to his theory, they weren't called black holes. That term didn't come for another 50 years. This is, again, like 1916. He thought, oh, yeah, this is a real mathematical solution. Everything crushes to a point. A region around which this crushed point forms, where we're not even can escape. And we call that a black hole. It goes dark.
How did he know to be looking for this? Meaning, what was the problem that Einstein was trying to solve that eventually led to our understanding of black holes?
So Einstein had been struggling to ask the question, if space and time are relative, what does that mean for the whole universe? And what does that mean for matter and energy that lives in the universe? And this is when he wrote down arguably the most important set of equations in the history of time that describe how space and time warp, stretch, react to matter and energy. And he threw it out there after many flawed attempts. He used to joke about how there were many incorrect papers with his name on it. And finally, they write down this consistent description. You tell me the matter and energy in the universe, and I'll tell you what the universe is doing. Even then, he wasn't the first person to say, oh, wait, the universe is expanding. That's what it's doing. He was shocked by that. He thought that was wrong. He fought the Big Bang. That's a whole other story. Same thing with the black holes. Somebody else, his name Karl Schwarzschild, was a German infantry soldier during World War I. He was on the Russian front. He had enlisted. He was also an astronomer. And he wrote Einstein this crazy letter, said something to the effect, I mean, it was unreasonably chipper, like, the war has treated me kindly enough. I've had a moment to wander through the land of your ideas. This is the kind of letter you write from the Russian front. And the problem he was asking is, what if the matter was all crushed to a point? He didn't say how. He didn't say if it was possible. He just said, imagine. Imagine I took a star, I crushed it to a point, and I just asked, what does the space-time do around it? That's all. And it's probably just a fantasy. It's just the simplest thing he could attempt, believe it or not. To crush all the matter to the point was the simplest mathematical solution he could find. And within a matter of 6 months of Einstein publishing the theory, he hands him really everything, essentially, we know about black holes in mathematical form. And it was incredible. It wasn't called a black hole for another 5 decades, but Einstein, he thought this was right. He helps him get the paper published. Schwarzschild dies on the Russian front like 6 months later, never knowing the impact of his ideas. But Einstein thought nature wouldn't make them in reality. Einstein thought, oh, it's just a mathematical oddity. How is nature going to crush matter to a point? I mean, how's it going to do that? That's silly. It's hard to crush things. And that was the prevailing thinking for a very long time. until people started understanding this whole thermonuclear fuel thing. It was really Oppenheimer, who was working on thermonuclear physics, who connected, not only working on the Manhattan Project, but connected that stars were doing something similar. And Oppenheimer wrote a very important paper where he predicted that, in fact, stars would make black holes in 1939 when they ran out of thermonuclear fuel. Not that they run out of thermonuclear fuel in 1939, but he wrote the paper in 1939 and he publishes it on the day that the Nazis advanced on Poland. And so it fell into obscurity. But
We were busy with other things.
We were busy with other things, as was he, like the Manhattan Project. But it was just one of these moments in history where the scientists were thinking about the same thing for very different reasons. Stars, war.
Star Wars.
There you go. And so, yeah, that's what brought us really to the point of thinking about black holes as real objects. And then we start to see them. We start to see them as the death state of stars. Very, very heavy stars, when they run out of thermonuclear fuel, they have a very dramatic end. They suddenly aren't burning so much, and they can't keep that pressure up. They collapse under their own weight. And this is, Penrose did this in a very abstract, very elegant calculation, showing that this would happen. And they collapse to the point where the space-time is so highly curved that not even light can escape the well. All light that veers too close will fall in to this well created by this collapsing object. And eventually, we call that the event horizon, the region beyond which not even light can escape. And eventually the star itself keeps falling. What happens to it, honestly, we just still don't know. In the interior of the black hole, we don't know what happens to it. But it leaves behind this inescapable sort of siphon. We probably have 1 billion of those in our galaxy.
I want to zoom in on one of these components that you're talking about with a black hole, and I want to see if you can help us understand. What does it mean to say what you said about space and time? And, you know, this delightful book, which literally fits in my pocket, does a really, really great job of kind of explaining space and time in very, you know, kind of simple terms so that you can build complexity. What does that mean when we talk about a black hole? Because I don't know what most people think of as like, oh, nothing can escape. If you get close to it, it's going to suck you up like a vacuum. You know, like that's, and we think of that funnel shape, right? But what does it mean? How can I conceptualize something that is a star, which I'm like, it's twinkling, but I understand there's gas, right? It's going in, it's creating a new place.
Yeah, in many ways, the black hole is more like a place than it is like an object. So let's go back to the star. The star is also deforming space-time. Right now, we are trapped on technically you might say geodesic, more naturally we're inclined to say orbit, around the sun. And that orbit can be thought of as a groove in space-time created by the presence of the sun, where you can fall freely around the sun and just no engines. We're not firing engines. The Earth is not burning fuel to stay in orbit around the sun. It's for free. We are absolutely no engines, no energy. We're just falling towards the sun, but we're going so fast that we keep clearing the prospect of falling in.
And this, so think of a groove on a record, right? A piece of dust, a speck of dust on that groove will stay in that groove unless something is blowing it out of its orbit. Right. It's just going to keep going.
We could be here for a very, very, as we have been, very, very long time. And we are literally just falling along a natural curve in space. The curve in space was created by the sun. The presence of the sun. That's the Einsteinian way of thinking about this. Newton's way would be there's a gravitational force, and they seem similar, but there are different predictions from Einstein's theory that we can see. We can see the differences. Now, as the sun, if the sun were to collapse to a black hole, which it won't, it's not big enough. It'll kill us in other ways. But if the sun were to collapse to a black hole, our orbit would be absolutely fine. So there's this myth about black holes that they suck everything up. We would find us a perfectly smooth orbit around a black hole at a safe distance. We could orbit forever exactly the same. And so black holes do have circular orbits around them. It's just that you can get much closer to a black hole. So if you look at the sun, it's like 1.5 million kilometers across in diameter. If it were a black hole, it would be 6 kilometers across. To make it dense enough to create the black hole, it has to be really small.
Okay.
So I'm taking the entire mass of the sun and I'm crushing it to the size of a city. Okay. And once that's happened, now it's only 6 kilometers across. I can get really close to that thing without burning up. I could have an orbit 30 kilometers outside a black hole, like right on top of that black hole, and I won't be sucked in. It's a perfectly safe orbit.
I don't feel comfortable.
I would not feel comfortable. It would be.
But we're using kilometers. That's even your metric system.
I feel like I'm tightrope walking on
really
a
don't
very
know
high
miles.
building edge, and you just one slip and you're sucked in, and that's it.
Yeah, you don't. It's not. I mean, it would be apocalyptically cold.
But talk about how this applies then to the notion of space-time and why it's different when a star is collapsing.
So it's not. So in that sense, it's not fundamentally different. It's different by degrees. It's different qualitatively. So the sun has a lot of the kinds of orbits a black hole has, but the more interesting orbits are only when it's so small that you're in so close that it gets more and more conspicuously relativistic, and you start to see much more unusual phenomena that you can't see because the sun's just too diffuse. It's too big, 1.5 million kilometers, all that mass spread out.
Got it.
It's just more diffuse, you know. But if you crush it down to 6 kilometers, the mass of the sun, then everything we're describing, the orbits, our curves in space-time, the curves just become more and more dramatic, harder and harder to find ways away. Requires, if I want to leave this orbit, I can send a satellite traveling with some fuel, and I can send it past Jupiter. We've done these things. If we were very close to that black hole, that would be really hard. It would be energetically cost a lot to get further and further away. So it's really just a matter of the degree becomes dramatic. And eventually there's a region where you would have to travel at the speed of light to escape. And that is just not something we think matter can do. And
So
then everything falls in.
Right. So
then you're in the
have
territory.
we sent things and they just get sucked up?
We have not sent anything near a black hole.
Right.
But we see things getting sucked up by a black hole.
Okay.
So we've seen black holes often come with stellar companions. Stars can come in pairs. One of the stars dies, becomes a black hole, runs out of fuel, becomes a black hole. The other star now has this very dense object in the material. It starts to cannibalize its companion. We start to see black holes destroying their neighboring stars and things like that.
Starts to ruin the neighborhood.
Yeah.
Now, all stars don't become black holes.
No, about 1%.
Why?
It's about how massive they
massive
are.
they are.
So our sun, when it runs out of fuel, it'll go through some period of collapse and expansion, but it's not heavy enough to overcome how hard it is to crush things, right? It's hard to crush things.
And how Valerie's asking, how do we see this?
So
It's like a big telescope.
So this was first observed in X-rays in the 60s and 70s. We saw they're called X-ray binaries. We saw essentially a black hole that looked like it was tearing apart its neighbor. And we saw
What
the
does that
light
look like?
it looks like bright flashes of light in X-rays coming from a tiny, tiny, tiny region. And so you're deducing how much mass in a small space. So one of the things about black holes, we think of these huge monsters. Point of black holes is they're spatially small.
In the same way that we can make descriptions about the Big Bang from the light that we see, right?
Yeah.
The collection of matter.
Yeah.
In those same ways, we can use those same methods to say something's going on here.
Yeah.
There's an enormous mass. There's light coming off of it,
Right.
and we know that comes from an expenditure of energy.
Right. Very good. So you say, look, I'm seeing, I'm seeing a tremendous amount of energy coming from a very, very small space
Right.
that seems to have a lot of mass. And that combination is when people began to say, you think these are black holes? Because they couldn't find anything else that could have so much mass in such a small space and be responsible for such energy. The light you're seeing is not coming from the black hole. It's coming from the destruction of the neighboring star. And so that is how we see black holes powering jets that are larger than the galaxies in which they reside. These are magnetic jets, like literally like ray guns, blasting highly charged particles into these huge jets that can go billions of light years across. So that's a tremendous amount of energy and power originating from a very small source, again, a black hole. And now we can look at stars from the center of our galaxy, and we see them orbiting something that's 4.5 million times the mass of the sun. These supermassives are different than dead stars. We don't know where they come from. 4.5 million times the mass of the sun, and it's very small. I mean, solar system sized, but if you think about the mass of the sun, you think it was only 4.5 million times the mass of the sun. It's only about 17, 18 times the size of the sun across. So you're jamming in that tiny spatial region 4.5 million times the mass. And that's when you get a black hole. So we see this black hole at the center of our Milky Way. It's 26,000 light years away. You can see the stars orbiting it. And you're like, well, what's that? There's nothing there. I can't see anything. And you say, oh, it must be a black hole. And now more recently, we've literally taken a picture.
What does it look like?
It looks like, it's called, the project was the Event Horizon Telescope. It looks very smudgy because it's hard to do. It's only a few pixels. But what we see is the ring around the shadow cast by the black hole. And the ring is from debris that was hot, that was falling in. And it casts the shadow, essentially, of the black hole.
I want to ask you a very emotional question. For you, as an astrophysicist, what is that like the first time you got to see the visualization of a black hole?
Well, I have a special connection to that particular project. So both as an astrophysicist and just as a person, the principal investigator, the director of that project, Shep Doleman, was a roommate of mine in graduate school. We went to MIT together, and one of my favorite all-time people. I mean, just a complete nut, incredibly creative person, and not a normal path, even in physics. He was sort of, I knew he was going to land something tremendous, but he was an outlier in many ways, creatively and imaginative. And he has been talking about this project since then, and had dreamt of it and thought about it, and then made it a reality. So when there was a press release and an invitation, I get an invitation from Shep saying, I think you should come to DC. I mean, we all knew what it was because there was only one thing they were trying to do. There was a twist. There was a twist in the result, but we knew they were trying to take a picture of the event horizon. It's called the Event Horizon Telescope. So really, it's just the shadow of the black hole. And there's only two candidates. And the surprise was that it was the other candidate. So the two candidates are our supermassive black hole, called Sag A star, because it's in the direction of the constellation Sagittarius from the point of view of the Earth. Are you a Sagittarius? Yes. And the other was a very big galaxy, a whole other galaxy, M87, that has an enormous black hole. It's much bigger than ours, over 6 billion times the mass of the sun. But it's so far away, it's about the same size in the sky. You know what I mean? It was like a similar candidate, M87, or sometimes called M87 star. We indicate black holes with the star moniker. And it was M87. I couldn't believe it. That really surprised me. But yes, it was a tremendously moving moment. And also just kind of surreal. Like, really, what was most surreal about it, since we anticipated the result, was feeling like a billion people, in that moment were looking together at this nothingness at the center of our galaxy that we orbit, right? And that might have something to do with why there are habitable regions in the galaxy, I mean, it's just, there was that moment, that kind of vertigo. Yes, it's a big day.
Yeah.
Philosophically speaking, what does it mean to you or the average person that there's nothingness at the center of our galaxy?
Philosophically, I mean, I think this idea of the nothingness of black holes is something I think we're still trying to understand. Objects in the ordinary sense are all slightly imperfect, or if you don't want to say that, they're features, distinguishing features. And that's true even with the most finely crafted Swiss watch. It really always has some fundamental distinction, even if it's at the microscopic level that I can't easily detect. Ordinary objects are unique. Black holes are indistinguishable from each other in a certain very profound way that we only see at the level of subatomic particles. And that has to do with the fact that they're really nothing. They're not made of, their atomic content's unimportant. Whether there's atoms in the interior or not is unimportant. They have this flawlessness hidden behind the event horizon. The event horizon cannot tell us anything about the interior. And in its intensity of obfuscating the interior, it makes this flawless veneer. And that means black holes look the same if they have the same mass, regardless of what they're made of.
Because nothing is nothing.
Because nothing is nothing, and they're indistinguishable, and the event horizon won't let us know if there's any distinction. If they were all made out of encyclopedias or all made out of some weird element or just made out of light, you can't know this.
But they start from a star.
They start from a star, but what is made in the end is something.
But just like nothing made a star can make nothing.
That's good.
Thank you.
And so that's that facet of black holes, which also Penrose contributed into understanding it. There are these things called no-hair theorems, like black holes can't have hair, they can't have distinguishing features. This idea that they're similar to gigantic fundamental particles, I think is very profound. I think it says something about black holes' role in the fundamental theory of the laws of physics that is not played by anything else at macroscopic scales. So yeah,
there's something you said, and it's not a coincidence, to have the Manhattan Project kind of square in the middle of,
right.
For most of us, like our history. And, I think that just like we just kind of talked about, that nothing can make a star and a star can make nothing, right? Can you sort of explain how, like, creating a nuclear bomb, right, is taking some very fundamental and phenomenal things about the natural world and,
right.
kind of cauterizing them, right, in this very terrifying way.
Yeah, well, it's E equals mc squared, and that's what a nuclear bomb is probing. So E equals mc squared, the most famous equation of all time, is the idea that there's energy trapped in the nucleus of an atom, but essentially everything has energy. One way you can think of it is it's the energy we all have just moving through time. It's like the energy of our existence in some sense. And people didn't, it's a tremendous amount of energy, E equals mc squared energy. That's why you want to make a nuclear bomb, because the energy you can release, let's say you fuse two elements and you make something whose mass is less than the sum of the parts. So some of that E equals mc squared, that mass energy, is what comes out. And it's so huge what's trapped in these nuclear particles that you have the potential of a nuclear weapon. It's also why you have the potential of a star, which is a tremendous amount of energy radiating for billions of years. If you think about that, what power you're talking about. So we're able to understand these things before we understand them. There's a great line in this play, Copenhagen, by Michael Frayn, where he attributes to Niels Bohr, the great quantum physicist, Danish quantum physicist, the line he says to his wife, "I don't think anyone's thought of a way to use quantum mechanics to kill somebody." And of course, this on the cusp of the nuclear weapon, and he does become involved with the Manhattan Project. So at first, it's just a dream about moving through time and the energy trapped in just the existence of matter, moving through time. It's base energy. Basically, anything we can understand, it seems like we try to harness. This is back to our opening conversation about being a technological species.
Well, I mean, also, you can take it one step further. Everything that we try and understand, we harness, and then it can be used
against us.
Right. I mean, I think of that, just because I'm kind of a Luddite, I think of that even in terms of technology. I thought it was unbelievable, to have a desktop computer when I was in college.
Yeah.
Like, it was the first ones, and,
Right.
and then I thought it was amazing to have this phone, in the palm of my hand.
Right.
And I mean, we haven't changed in terms of our, evolutionary capacity in the last 10 years.
Right.
But what we've seen is a complete hijacking,
Right.
right? Based on an adaptation
Right.
that has become a compulsion.
Yes. I mean, I guess it's another one of those examples we're saying, our mandibles changed, our upright stance, our birth canal became a hazardous proposition, but all of this in reaction to our tools.
Right.
So are we on some strange evolutionary path where really we really will be fundamentally biologically different?
It's funny because, and it's a little bit, obtuse, but there was just a piece in The Atlantic about Gen Z and how they date and how they fall in love. And most Gen Z is what, 97 through, it's our kids.
Yeah.
But
I have a couple of those.
Yeah.
Yeah. I made a couple of those.
Right.
Yeah.
What they said, or what they kind of revealed in a series of really fascinating and tragic interviews, is that young people would rather have sex than hold hands. That most people consider, of this generation, most people consider that a completely standard gesture, intercourse. But the notion of intimacy, of emotional intimacy, of holding hands, of asking someone, "Will you be my girlfriend?" is so terrifying. And I was thinking, what is that we've evolved to, right? And I think it's a similar kind of line of questioning. You don't have to answer that, but
yeah. Well, I hate to invoke the AI because those conversations have not progressed. Well, it is one of those examples we also talked about in the beginning where you're circling around the same drain.
Yeah.
And very rarely does somebody say something that gives me pause where I think, oh, I haven't heard that before, But this is a new, even the Zers will distinguish themselves from the generation that's growing up with this. And this is that whole phenomena that the technology escalates so quickly that the difference between two people in the 11th century and the 15th century, not as huge as 1980 and 2025.
And we've seen how this movie ends.
Yeah.
Like, we've literally seen what happens when the machines take over.
Yes.
We all get sucked into a black hole.
Yes. I do wonder, the machines for me right now, I really do think these are very interesting, but they're just computing this probabilistic thing. That I don't see anything going on there yet. I understand that regardless, though, they're really powerful. I think that's one of the things that chills me is I don't know that consciousness is a requirement of something that can compute very well. Right? Consciousness is a requirement of something that doesn't compute very well. I should be asking you, but my impression has been like because of our poor computational power, we have to approximate.
Right.
That's a child, that's a chair.
Right.
Right? That's very hard to teach something with
that's
a lot of
also
computational
art, music,
power.
love,
Right.
creativity.
That's
Like
great.
that's what you get. And that's
Right.
what you don't get when you, I mean, I don't mean to be this person, but you don't, when people are like, oh, it's the thinking, it's like, no, it's not. It's amassing all of the information that exists as zeros and ones.
Right.
And it's spitting out a probability.
Right. And that's very powerful. And maybe
It's
maybe it'll
wonderful.
even be a kind of thinking. And maybe one day I'll love my AI and I'll be sympathetic and nostalgic about my AI. But I don't know that it will ever need consciousness in the way that we do if its computational power keeps getting better and better.
What Robin Hanson would say is we don't need consciousness, and soon we'll all just be, I can't even articulate it. We'll just be AI interfaces interfacing with each other.
Right.
And I'm like, I don't think I evolved to this point,
right,
or that we evolved to this point for that to be where this story ends. I don't know.
Does the AI need the qualia of the experience of yellow?
Right.
Does it? Why would it need that? Maybe it's just, okay, I've measured this energy and that's sufficient.
And it has access to all the variations of what yellow could be, so it could just pick a point and then have that. It doesn't...
and converse about it really effectively, and that's a kind of a thinking.
Yeah, but
it might never have qualia.
It doesn't have the experience of when you see this.
Right. Yes, exactly.
It doesn't have that
image of the black hole.
Yeah.
No, but it will fake it really well to the point where we wouldn't really understand the difference of it. Is it actually having it, or is it just representing to us that it has it because that's what it thinks we want?
Right. Why not emulate the reaction as well as it's emulating the language describing the reaction? All of that can be programmed in this by, the AI can program itself in this black box of these learning algorithms. And again, all of that's fine. What will it matter whether or not it has a conscious experience?
And its drive for self-preservation is not a sign of consciousness necessarily.
No.
It's a sign of
Copying
replicating our drive for self-preservation and how we would go about that same task. So it's just an amazing mirroring agent.
Yeah, I get very worried when people are like, it's thinking, it's knowing, it's feeling. No, it's really not. It's it's a really fancy abacus.
What has happened recently that black holes are being talked about so much? Is it that there's the picture? What has evolved that it's become part of sort of a common consciousness or awareness now?
I would say towards the end of the last century, the end of the 1900s, people were thinking black holes might start to fade in terms of their scientific importance. And I remember I was very excited about black holes. I was all about black holes in graduate school, and people were like, what are you doing? Come on. We sort of know everything we need to know. Where are we going to go with this classical system? And then a lot of things happen. One of them is purely theoretical, and some of that is observational. So yes, we started to see the stars orbiting the center of our galaxy. People watched them patiently for 16, 17, 20 years and deduced that there was a supermassive black hole. That was a surprise because that doesn't come from dead stars. These are new. We don't know where they're old. They're probably the oldest black holes in the universe, but we don't 100% know where they came from. Probably skipped stars altogether, directly collapsed in very diffuse material in the early universe, So these are fascinating. Then there were these other, just other observations like that, beginning to understand some of these very powerful engines. This was earlier, but these things we see in the farthest reaches we call quasars, most powerful, brightest beacons, most powerful engines in the universe, and they're probably, I think very confidently sourced by black holes. And then these recent things like taking the picture of the black hole. And so the conversation now is an active one of science. How did they form? What effect do they have on the galaxies? What's the role that they're playing? Will we all end up falling into black holes? So there's all of that astronomy. Good old astronomy. The rest of the world might not continue to be as interested in it as we are. And then there's this theoretical stuff about black holes being fundamental. That, I think, is a real driver for people who want to understand quantum laws of physics. They want to understand quantum gravity. They want to understand if there truly is a theory of everything. They want to know if string theory is right or wrong. And black holes are your terrain to understand all of that.
Are there more black holes forming, or we're just being able to observe them more?
Yeah, there are more forming. So there are star-forming regions, so there's more stars forming, and some of those will be black holes one day. So it's really about how massive the star formation is. And maybe over time, there will be less stars forming and less very, very massive stars forming. But in our galaxy of its hundreds of billions of stars, about 1% of them are big enough to become black holes. And
what about other galaxies? Do we know about black holes?
Yeah, probably about the same. This is part of that we're kind of unique, but not so unique.
Sure.
We expect other galaxies to be made of atoms, to reflect light, to have the same thermonuclear properties in the cores of stars. And so, we expect about 1% of those to make black holes.
Are we all going to fall into a black hole?
It's possible. So we're in orbit. The picture that we just discussed one of two pictures that have ever been taken of actual black holes. We are in orbit around that black hole, very slow. And eventually we could fall in.
Slowly drifting into it?
No, we're orbiting safely like we are the sun. And the entire solar system is going together. Our whole solar system together orbits the black hole. And when Andromeda crashes through our galaxy, we might have collided before, we'll probably collide more than one time in the future, our black holes will merge eventually.
What does that mean when galaxies collide?
Yeah, so largely they pass through each other because there's a lot of empty space between the stars.
But what distinguishes our galaxy from another galaxy? It's not like there's a border.
Well, that's a good question. It drops off real fast. So
it drops off real fast.
Meaning the density of stars.
Oh.
And so our galaxy looks like this spiral Milky Way.
Yeah.
Then there's a lot of nothing between us and Andromeda. Pretty empty. Oh. Real nothingness out there.
How far?
That's a couple million light years and 55 million light years to M87, which I mentioned. And these are close. These are our close neighbors. These are the ones that are behaving oddly because we're all so close together.
So what would that be like when
So billions
galaxies collide?
of light years apart are other galaxies. And we're only going to collide with our local friends in our Virgo cluster,
Do planets
it's called.
smash into each other?
Not likely, terribly unlikely, because there's just so much empty space.
That doesn't feel definitive enough.
Well, I guess it's possible. It's not zero possibility. It's just
I'm
unlikely.
going to run the stats on that. If you think, if you just told me there's so many stars and there's so many planets and there's so many moons,
but there's a lot. So
a lot of space.
There's a lot of space between every star,
right?
And that's why they look like tiny dots and not a wall of brightness. They look like mostly darkness with a little twinkle.
But statistically speaking, the more there are, the higher the probability that something will.
Right, and they're still really sparse.
That's amazing.
Yeah, really a lot of empty space. But there's a lot of gas and dust, and that stuff will collide, and that'll light up. But mostly the stars will miss each other, very likely.
Okay.
And if you look at simulations,
like ships passing in the night.
Yes, really. And some of the stars might get thrown out of the galaxies when this happens, just from gravitational.
Would
whiplash.
The sun get
So the
thrown out of
simulations show our solar system staying together pretty comfortably. Like we stay with our sun. And we get kicked around into a different orbit around the center.
Okay, let's have a catastrophic question.
Right.
What if the moon, what if the sun gets knocked out of its orbit? Does we die?
We're going to be knocked out of our orbit around the black hole. As long as we stay in orbit around the sun, wherever it goes, as long as we go, we're okay.
Okay, so because we're tethered in a sense.
If we part ways, it is all over.
But we
need the sun. We will ice over.
The title of this episode is "We Need the Sun."
Yeah.
Understood, but our orbit around the black hole could change.
That's fine, as long as we stay with the sun.
And will that have any effect on us?
I'm sure there are unforeseen consequences, but more or less, as long as we're within the sun's magnetic solar influence, we're probably largely okay. And if we were to fall into the black hole, we'd all go together with this. It's not like it's going to pluck us separately.
I'm sending
like
you
a piece of lint from the, solar neighborhood. But we're very stable. It's this thing I told you. Black holes aren't vacuuming things up at 26,000 light years away. You're fine. There are things in orbit around the black hole. These stars we talked about, they're fine.
He likes things to be worried about. What should he be worried about?
What happens when you do get in a black hole? Explain how time changes.
Yeah. So one of the most beautiful results that goes all the way back to when Schwarzschild first found this mathematical description was this idea that time appears to slow as you approach the event horizon. And let me clarify what that really means. If you and an astronaut are in a happy space station together, and you are in some safe orbit outside the black hole and you're monitoring it, fine. One of you jumps in. As you approach the black hole, you have beautifully manufactured NASA watches and they're perfectly synced. One of you falls into the black hole. As you approach the black hole, your watch will appear to run slowly, according to the person who's safely back on the space station. But so will your breath slow down. So will your biological functions. From your point of view, your clock is just fine. Okay, everything's synced, just fine. it's the person back on the space station seems to be going really fast and seems to be aging really quickly. And their hair is turning gray and their clock is whizzing and music's playing really fast. And all of these things are happening as you approach the event horizon. Now, as you get to the event horizon, your time has slowed as much as it possibly can. To the person who's now aged 100 years, in the time you've aged, let's say, a minute, however long it's taken you to do this dramatic fall, thinks you've frozen. At one point, they were called frozen stars because they didn't understand what happens when you cross this boundary. And it seems to them that you actually never quite make it across. Now, eventually, your mass will deform the black hole enough, and maybe after 1 million years, they'll be like, oh yeah, they're gone. But from your point of view, the whole thing took a minute.
That's like in Contact, when Jodie Foster has like this entire experience and she sees her dad and she meets God and blah, blah, blah. And she comes back and they literally said, you disappeared for 10 seconds.
It's like every near-death experience we've heard of.
Yeah. And well, Interstellar also represents this by my good friend Kip Thorne, who's also nearby. Kip won the Nobel Prize for, we didn't even mention that detection, the detection of collision of black holes. And he wrote the treatment for Interstellar. So that Interstellar, he really thought about the physics of that. It was his idea to make this crazy movie. So to the person going across that's the interesting person. And that was not understood for a very long time, that what happens to them? Are they really frozen there? And relativity suggests that they're seeing nothing unusual. So how are they hanging out there? And actually, as far as they're concerned, we call it no drama. They had an experience as unspectacular as stepping into the shadow of a tree. And they crossed right over. And they didn't know. Nothing terrible happened to them. If the black hole is big enough, they actually don't get torn apart, which might seem counterintuitive. They can drop across just like a pebble. And then it unfolds, and then they're in trouble. Then they might start to notice things are looking weird. But black holes can be bright on the inside, even if they're dark on the outside, because light can fall in behind them. Nothing's stopping the light from coming in.
Just can't get out.
So they can see the space station and going through and falling apart and millions of years passing, and they can see the galaxy evolving, all these things happening very quickly as they approach the singularity. And there, our description breaks down terribly. Nobody really knows what happens in there, but survival is absolutely not. As I say, the Black Hole Survival Guide title is spoiler alert, it doesn't end well. Yeah, does not end well.
If I put on just my magical thinking hat for a moment, if we can understand how to create a nuclear bomb by understanding stars, can we understand how to slow aging by understanding some of the impacts of black holes?
Well, here's the thing. We are aging more slowly on the Earth for the same reason. It's just not as dramatic. It's this, again, it's more extreme in kind with black holes. But it is the case that the Earth's curvature causes time to change as well. And we are aging more slowly on the surface of the Earth than we would if we were very far from the Earth and away from all other planets. So that is a measurable effect. And there are other relativistic effects that have to be corrected for with all of our GPS units for Lyft or Uber to pick me up on the correct corner, right? This is measurable and factual. It's not just something that's so theoretical. The reason why it doesn't do you any good in terms of longevity is because you're synced with the clock. You're not getting any more out of it. A minute on your watch is a minute for your experience. There's nothing special about your watch in this. Literally, your time is changed relative to someone else's time. All of it has changed. So you don't get more out of life.
I'm just imagining that you could harness some black hole energy into a chamber that I sleep in.
Right.
But it's not the energy, it's the
experience of it, not.
Yeah, your experience of it is the same. Even if somebody felt 30 years pass for the one night you slept well, you'd still have that one night's sleep, right? No more. You weren't able to get up, live 30 years of life. You got no more out of it than that 8 hours in your experience. And so, in that sense, but what I could do is I could freeze you. You have a terrible disease and you want to wait until there's a cure. And so I don't yet know how to travel to my future, but I know how to travel to your future or get you to travel to civilization's future. So I could park you near a black hole. Your time will slow down. 200 years later, we have a cure. We bring you back.
New business idea. Human parking lots.
Elon Musk is barking up the wrong tree.
Yeah.
Where can people find out more about you and all of the incredible writing you do?
I really appreciate that. This Substack venue is new for me. I really, I don't think of myself as short form, turning around pieces. Substack is aiming a little bit more for long form. I guess we're meeting in the middle. But this idea of thinking about things and just communicating has been really fun. It's been an unusual experience. It's allowed me, after our conversation, maybe I'll go back and think of something that was sparked literally by us talking. And whereas that used to kind of disappear into the void, I'm finding an opportunity to collect those reflections.
That's great.
So that's really been fun. The last piece we were just talking about is about how we radiate as hot bodies. And I wanted to bring you my hat, which I made with Planck's law on it, to match your nerdy, wonderful brain hat that I saw when I walked in. So I think that's really a place. And also I do a lot at Pioneer Works in Brooklyn, which is an art cultural center in New York, and arts and science place where science is a pillar in a cultural institution. And that's been a really long-term project and labor of love. And we do a lot of events, talk to Nobel laureates, talk to scientists of all varieties. And we have people in the hundreds packing a sort of cool place in Brooklyn. It's kind of what you said at the beginning of the conversation, because they want access to this level of understanding. And they want it for emotional reasons, poetic reasons, not because they're going to graduate school. They want it to make sense of their lives.
Yeah. They're not building the human parking lot startup yet.
Yeah, right. We'll be starting that after today's talk.
We also started Substack and found that it's a really cool place to expand
I've been
on a lot of
checking you
ideas.
out there. Yeah.
So we recommend people check yours out and tag us if you come up with any big ideas from this conversation. As we depart, anything that has really surprised you or sort of made you wonder in the last little while that you want to share with us as we say goodbye? Yeah,
I've been working with my scientific collaborators, Brian Greene, Massimo Peratti, Daniel Cabot. I mean, I have the pleasure of really working with geniuses. I mean, honestly. We've been thinking about a universe with extra dimensions, which many people have thought about since Einstein. If you're going to talk about space and time, why 3 space? Why 1 time? And I've been astounded at looking at some of these, we call them topological spaces, some of these very peculiar geometries in this higher dimensional space, and how it could, even if there are these tiny curled up origami dimensions that we can't probe. They're on the quantum scale. We can't point to them. We don't occupy them. They could leave an imprint in the Big Bang. They could leave an imprint in the particles that we see that are allowed in the spectrum of possibilities. They could have something to do with primordial quantum black holes. I think that has been very fascinating, chilling. You have this moment of feeling like you have a glimpse of something maybe nobody else has ever seen. And then it's very fleeting and fugitive and hard to get your hands around.
Are there any updates on the handedness of the universe?
Well, exactly part of this project was about the handedness of the universe.
What does it mean to say that the universe tends to be left-handed?
So literally, if you have a left-handed glove, you know it does not fit you properly on the right hand. And in particle physics, that refers to a subtle quantum property called spin. Things can spin in a left-handed way and that cannot be turned into a right-handed spin. But it's just like saying a left-handed glove and a right-handed glove. For reasons we don't understand, most particles interact left-handed, predominantly, especially one interaction called the weak interactions. We don't know why. It's left-handed. It's chiral. is how we say it. What's wrong with the right-handed guy? Why doesn't it feel the same interaction? And we think dark matter could be right-handed, and that's why it's evading us. There's so part of these extra dimensions is that I can send things in these strange topological spaces left-handed, and they can come back right-handed. It was a game we were trying to play. It isn't the most interesting thing that we ended up discovering about it, but yeah, these are. Every theoretical physicist interested in particle physics wonders about the chirality of the universe.
It's very hard to talk to you for only a couple hours.
I thank you, I think.
Thank you so much for being here.
Thanks so much for having me.
So much fun to get to talk to you.
Yeah, really fun. I wish I had a cool t-shirt, and I wish I had my hat. Till next time. Thanks so much for having me.
Thank you.
A lot of these interviews, people will say stuff and then they're in the flow and I'm like trying to make notes and write down things to circle back on. But she was like, no, our sun isn't going to turn into a black hole. It's going to destroy us in other ways. Wait, what? We didn't talk about, she didn't explain that. Is that going to happen soon? Should I be worried? How concerned am I supposed to be?
Is this the conclusion that we're doing?
Yes.
Oh, we're in it? Oh, we started?
We got to keep that.
I didn't know we started. It's a little bit casual. The only way that we would all incinerate is if, when the galaxies collide, it knocks the sun out of orbit and we go with it. And then we're sucked into a black hole. But it's not very probable that'll happen. You know what, Janna? That's not enough assurance.
While there is a lot of empty space, I'm sure a couple stars are just going to bump into each other and explode.
I
am sure I have no calculations.
It's the end of never-ending story. Do you remember what happens? Anyone out there?
No.
Things start colliding. They're blowing apart because he doesn't name the princess. And all the things are colliding. That's what I pictured.
It's a deep cut I don't have a reference for.
Oh, goodness gracious.
But also, our closest neighbors are slowly encroaching on us, but our faraway neighbors are too far. It's just a lot to process.
I was mostly thinking, how does she keep all those numbers in her head? And then I thought about all the things I know about the brain, all the different structures and all the different tracks. I guess you know what you know, but I'm like...
if we were to ask you about song lyrics, you would just have an endless supply of information.
Well, we had someone on the other day who was like, locus coeruleus, and I'm like, I know where the locus coeruleus is. I've dissected that. I know where that...
Where is it?
Well, it's back here. It's a Pons thing. And it's blue. It's cerulean blue. Anyway, but I was like, I don't think that we truly really can understand what she's talking about just because of the sheer numbers. 6 billion light years, 8 million kilometers of, it's I can't. This is really, it's, I don't know if I can even explain how sweet this book is. And also there's this beautiful art. And so it shows, here's what you were asking about, how time changes when you're traveling. It's just all these beautiful illustrations of all of these really enormous concepts. It's really beautiful. So I recommend the Black Hole Survival Guide.
Also, it's not bigger than 7 inches, 8 inches.
No, literally, it's the size of, it's the size of what I wish my cell phone was. Hello. Make sure to follow us on Substack and check out Janna Levin's Substack page as well. From our breakdown to the one we hope you never have. We'll see you next time.
It's Mayim Bialik's breakdown. She's gonna break it down for you. She's got a neuroscience PhD or two. One fiction, and now she's gonna break